All right, this is a quick lesson. We shouldn't take too long. So we're going to look at a quick recap of a neuron. This is the motor neuron. You might recognize it with the cell body and the dendrites coming out of it, with the long axon and the axon terminals. But this could apply to the other neurons as well. Let's just look at this generic neuron here anyway. So we need to be able to understand and explain how a myelinated neuron allows for a quicker speed of impulse, which is useful because that means you can respond to a stimulus quicker. So the quicker the impulse can travel down the neuron, the quicker you can respond. So keywords are myelin sheath, Schwann cell, nodes of Ranvier, saltatory conduction, and axon. So you need to be able to describe the structure and function of a myelinated neuron. So let's start there first. So this neuron here, these little blue structures here, these are made up of a type of cell called a Schwann cell. And it's a bit like getting a pencil, and if you were to put that pencil into a piece of paper and then roll it up, you can see there's our axon. If you imagine that being a pencil, the cell is like a really long sheet which wraps around. And what that does is it's providing a lot of layers of cell membrane. This one there, cell membrane. So it's acting like the wire cover of like an electric cable, that insulating cover. So there it is there again. You can see it's a really good insulator, and that's going to make it impossible for sodium ions. Remember the sodium ions that can diffuse in during action potentials? They can't get through all these barriers. It's too difficult. So the only place that the sodium ions can diffuse into the axon is here. It's basically the little gap where each node of where each Schwann cell is meeting each other. So where each myelin sheath is meeting. So these little gaps here, they are called nodes of Ranvier, and that's the only place where sodium ions can diffuse in. So when we talked about the axon before, we talked about how if sodium ions were to diffuse in, that's depolarization, this depolarization will cause another depolarization, which will cause another depolarization, and so on, like a Mexican wave. So when there's no sheath, although this is still really quick, it's a little bit slower because we have to go with one at a time, one after the other. So there's our unmyelinated sheath, or unmyelinated neuron. And now when it's myelinated, here is one wrapped up Schwann cell, another one. So now let's do another one as well here. Now the only place that the sodium can enter is here, and here. And that's equivalent to, imagine a Mexican wave of one person after the other. This is more like every 10th person, rather than all the 9 people in between doing it as well. It just jumps from 1, 10, 20, 30. So it's going to be much quicker. And that's essentially what's happening. So it's going to make it that bit quicker. All right. So that's how the neuron is being myelinated. It's been myelinated by a special cell called a Schwann cell, which is wrapping round over and over again around the axon. So let's just draw it again. There's the axon, if we're looking at face on, and the Schwann cell is wrapping round and round, making it pretty much impossible for sodium ions to be able to diffuse where the Schwann cell is. Okay. So we've explained why the myelinated neuron has quicker impulses. It's because rather than each sodium channel having to open one after the other, we can jump from one to the next. And this is why it's called saltatory conduction. Saltatory, yeah? So if you speak Italian, saltare means jump. So that's where it's coming from. Latin as well, I think. So it's the appearance that the conduction of the impulse, rather than being one long flowing, like this one here, flowing from one to the next, it appears to be jumping. So this one, if you were to look at it if you were to read the electrical activity, you'd see action potentials happen all day along it. Whereas on this one here, the myelinated, you're going to see activity doing this, action potentials, this jumping appearing that's taking place. So let's apply this to a question now. Okay, one more thing to mention as well is, although it's not mentioned in the title, you just need to be aware that not only does a myelinated neuron have a quicker speed of impulse, also an axon, there's your axon, one with a wider diameter will also show quicker speeds of conduction, because there's going to be less resistance for the flow of the ions, sodium ions. Okay, so you might get a question that looks like this. Here's your data. We've got type of neuron. We've got 3 myelinated and 2 unmyelinated. And we've got axon diameter and speed of conduction. So we've just talked about this one here. We talked about myelinated versus unmyelinated. So at this stage, you should already be aware that myelinated has a quicker speed of conduction. I've just mentioned the axon diameter. The wider diameter, the faster it is. Let's just double check. Is that the case? So speed of conduction for these first 3 is 25 meters per second, 30 meters per second, and 35 meters per second. So let's see how they compare with the unmyelinated. We've only got 3 meters per second, but this one actually at 30 meters per second as well is somehow matching with this one here. I wonder why that is. Well, let's look at the other column of axon diameter. In order for the unmyelinated to achieve this 30 meters per second, its axon diameter needs to have been 1000 micrometers, whereas this one only needs to be 10 micrometers. So in order for an unmyelinated neuron to achieve the same speeds as a myelinated neuron, the axon diameter had to be 100 times wider. So we can see the importance of myelinated. So using only the data in the table above, describe the effect of each of the following on the speed of conduction. So you state the obvious. The obvious thing first is myelinated neurons, or myelination, produces a faster speed of conduction. What else could we say there? We could say that an unmyelinated neuron, in order for it to be able to have a higher speed of conduction, it's going to need to have a very high axon diameter. So there's your obvious one, is that the myelinated is faster. Okay. Then axon diameter, what can we mention here? Well, obvious one, the bigger the diameter, the faster the speed of conduction. And we could perhaps compare these bottom 2 here. We've got an axon diameter of 15, an axon diameter of 1000. You can see that the speed of conduction is 10 times faster. So you could even mention that in your data. So that's it really for myelination. Just know how the neuron has been myelinated using the Schwann cell, and be able to explain why it's quicker. What is this type of jumping conduction, which we call saltatory?